Hi guys, thank you for clicking to my video. In the previous video we discussed about the 13C NMR and before that we learned about the proton NMR. Now I'm hoping that you watched all those videos. With those concepts we will now move towards the multinuclear NMR. Here also the proceeding is similar to that of the case what we have studied in proton NMR and 13C NMR. First of all we will see the basic properties of the nuclei. Here in this the name of the isotopes and its spin, like the spin number, we know already that those nucleus which are having the nuclear spin I is equals to half, they are preferred moreover than that of those which are having the nuclear spin which is greater than that of the half, as because those nucleus which are having the nuclear spin half, they are magnetic nuclei and are non-quadrupolar nature, so they gives a NMR signals. But in case of this I greater than half nuclear spin, this kind of nuclei, they will be non-magnetic and they does not show any NMR signals. So hence this nuclear spin, that is I is equals to half, they will be preferred moreover than that of those which are having the I greater than half. Now in this we will take one example in case of the heteronuclear NMR. Like other than that of the proton and the carbon, we will take the example of nitrogen. That is, nitrogen we have two isotopes, that is 14N and 15N. In case of 14N, its natural abundance is 99.63%, which is very high, but its nuclear spin is 1, that it is quadrupolar. What we have already seen, it's greater than half, so it is quadrupolar. It will not give NMR signal as it is non-magnetic nuclei. But in case of this 15N, which is another isotope of nitrogen, it's having its natural abundance 0.37%, which is very less, but it is having the nuclear spin half, which is magnetic and it's of non-quadrupolar nature, so it will give a NMR signal. So with that we will see the another properties like natural abundance, what we have considered only. Here also in case of nitrogen we can consider the example of carbon. We know that it has the isotope of 12C and 13C, where the 12C it is having the higher natural abundance than that of the carbon, which is having natural abundance, that is 13C carbon, which is having the natural abundance 1.1% only. So it is active. But in case of NMR signal we will consider only this 13C, not this 12C. So here the 13C's abundance is very less, so the natural abundance of magnetic nuclei should be high to give a significant NMR signal. Likewise they should have a high gyromagnetic ratio, so the higher gyromagnetic ratio is preferred over than that of those which are having the less gyromagnetic ratio, as it results to the relative sensitivity of the nuclei. Since we know that the relative sensitivity, it depends solely not only on the gyromagnetic ratio, but sensitivity it depends on the natural abundance also. So that what we have seen in the carbon NMR. Now with this brief discussion in the basic properties of the nuclei, in case of the heteronuclear NMR, we will now proceed to the nucleus with half spin, that what we have seen already, that is concentrated nuclei with high natural abundance, those are concentrated nuclei, and half spin nuclei, those are dilute nuclei which are having the low natural abundance. So on the basis of the different types of magnetic nuclei present in the molecule, we can classify all the molecules into 7 categories for stepwise learning of the heteronuclear, that is multinuclear NMR. Like number 1, we can consider molecules with one type of concentrate nuclei. Since we know the concentrate nuclei are those nuclei which are having the high natural abundance. Like in case of proton, it's having its natural abundance near about 100%. So it is concentrate nuclei. Likewise, other example we can take 103 rhodium, that is also having its 100% abundance. So with that we will discuss some other examples in the later time of our discussion. Here the molecules with one type of concentrate nuclei, it means that only one kind of concentrate nuclei will be present in the molecule. Like here in case of the fluorine. So fluorine, that is 19F, it's having its natural abundance about 100%. Proton, what we have already discussed. So here only one type of concentrate nuclei is there. Here also in case of P4, here phosphorus, 31 phosphorus, it is having its natural abundance of 100%. Similarly, here in this case of H2O, the proton which is present over here, which is responsible for NMR activity, so it's having the 100% abundance. Here also the hydrogen, that is proton over here, this will only show the NMR activity, as because other atoms, they will be those which are present, like chlorine over here, it is non-magnetic, so it will not give NMR signal. Those are giving the NMR signal, they are concentrate nuclei. So only one type of concentrate nuclei we considered here in this number first kind of molecule. In number second kind of molecule, we will consider those type of molecule which are having two types of concentrate nuclei. Like here we can consider an example of HF. H here, this is proton, it's having its natural abundance very high, that is concentrate nuclei. Proton, here fluorine also, it is having the concentrate, that is high natural abundance, so it is concentrate nuclei. PF3, both are having high natural abundance, so both are concentrate nuclei. Similarly here PF5, S3PO3, here this proton, it is having high natural abundance, so it is concentrate nuclei. Similarly, if we consider this this P over here, phosphorus over here, then this is having its natural abundance around 100%, but this oxygen, it's not magnetically active, so it will not give a NMR signal. So these two types of concentrate nuclei are present in this molecule, so this will fall under the second category. Similarly PS3. So likewise we can consider here, in the first case we consider only one type of concentrate nuclei. In second case we consider two types of concentrate nuclei. This all type of molecules we will discuss them later in a very detailed way. Right now we are just seeing the way how to go with this multinuclear NMR. Here in the third case we have the molecules with three types of concentrate nuclei. Here we studied two types of nuclei, HF, both of them are having the concentrate nuclei. Now here we will consider three types of concentrate nuclei. Like one example, we can consider this HPF2. So on this basis we can assume C, that is 13C H2F2, considering this 13C as a concentrate nuclei. So this is assumption based. With those example we can move forward to another category, that is fourth category, in which we will see the molecule with one type of concentrate and one type of dilute nuclei. Here we can consider an example of CH4, that is the carbon over here that will be present as a 13C, and we know that 13C is dilute nuclei. But in case of this 4 proton, the proton over here, it is concentrate nuclei. So here two types of nuclei are there, that is one dilute and one concentrate. So this is fourth category. Similarly, another one, CF4, fluorine over here, 19F. It's having the nuclear spin half, which is having natural abundance of 100%. But in case of this carbon over here, 12C, it's having high natural abundance, which is not an NMR active, but 13C is NMR active, but it is dilute nuclei. So with that, these are the two examples we can consider of this fourth kind. We will discuss that later. Now coming to the fifth kind of, that is fifth category of this molecule, we have this one type of dilute and two type of concentrate nuclei. Like here in this example we have carbon over here, they are 13C, which is dilute nuclei, but fluorine, proton over here, fluorine and proton, two types of nuclei, they are concentrate. So this is one example. Another example, we can consider this phosphorus over here, that is PCS3 whole thrice. So the phosphorus over here, that is 31P, which is having the nuclear spin half with natural abundance of around 100%. Similarly to that of this proton over here, it's concentrate nuclei, but the carbon, they are dilute nuclei. So two types of nuclei, they are concentrate, and one type of nuclei, they are dilute nuclei. With that we can see another category, that is molecule with one type of concentrate and two type of dilute nuclei. Here in this we have two types of dilute nuclei and one type of concentrate. So here in this example we have silicon. Since we know that silicon, it is having its isotopes as 28 silicon, 29 silicon and 30 silicon. So among that 28 and 30, they are NMR inactive, but 29 silicon, it's about 5% having the nuclear spin half, and they are NMR active. So this is having only natural abundance of 5%, that comes under the dilute nuclei. So in this molecule we have silicon as a one dilute nuclei and carbon over here 13C 1.1%, that is dilute nuclei. So two types of dilute nuclei with one proton over here, that is the proton over here, that is one kind of concentrate nuclei. With this brief overlook to the different kinds of molecule, they are categorized for the stepwise learning of multinuclear NMR. We will now consider the detailed discussion to these different categories. That is, first of all we will consider the first category, that is having the molecules with one types of concentrated nucleus. Since we know the concentrated nucleus are of those kinds which are having their natural abundance around 100% or equal to 100%. Like in case of the proton, which we are very familiar with, its natural abundance is around 100% and its nuclear spin is equals to half, so it will give NMR signal. Similarly to this kind of proton, we have another nucleus, that is 19F, which is having natural abundance 100% and its nuclear spin half, and 31P 100% natural abundance, 103 rhodium, it is also having its natural abundance equals to 100% with its nuclear spin half. So all this nucleus, they are 19F, 31P, 1H, 103 rhodium, they all are having its natural abundance of 100% with nuclear spin half, so they are concentrated nucleus. So at once considering this one of the nucleus, we will consider the examples. So coming to the point, considering the example, we have BRF3 molecule, which is having its T shape. Considering the bonding structure, we have this, which has been framed by the Bend's rule, where we have one equatorial fluorine, two axial fluorine. Now to this two axial fluorine, if we consider them as a first kind, then this equatorial fluorine will be of second kind. So we have two kinds of fluorine which are responsible for the NMR signal in 19F NMR. So we will get a 2 signal in 19F NMR. Now if we are getting clear to this point, then we will have the area ratio of 2:1, that is 2 fluorine are of one kinds and 1 fluorine of two kinds. So we'll get the area ratio of 2:1. Similarly, if we consider their multiplicity, then we have the multiplicity as for this 2 axial fluorine. This axial fluorine they will couple with this one and only 2, that is second kind of fluorine. So we'll get doublet signal for this 2 fluorine of one kind. And for this second kind of fluorine, at once it is coupling with the 2 fluorine of first kind. So we'll get 1 fluorine of two kind, triplet signal. So doublet, triplet will get the Pople notation as a AX2. Similarly to this, we will consider another example, that is of this one over here, that is SF4. Now here the shape of this SF4 molecule, it is of seesaw type, where this fluorine which is numbered as 2 and it's shown by this wedged bond, it is lying above the plane, that is towards our side. Similarly this fluorine, it is lying below the plane, which is shown in a dashed bond. And that of this fluorine which is numbered as 1, they are lying in plane along with this sulfur. This shape of SF4, it is obtained from this structure over here, which is given by the Bend's rule, where this lone pair of sulfur, it is lying in trigonal plane along with this 2 fluorine at equatorial position and 2 fluorine at axial position. Now if we consider one of this axial fluorine and see from this side, then we will be able to see one lone pair lying in a trigonal plane along with this 2 fluorine at the different corners. So we will not be able to see the fluorine which is lying in another side from this side of the fluorine. Similarly, if we consider this fluorine over here and look to the upside towards this trigonal plane, then we will be able to see the lone pair and 2 fluorine at the different corners. So that is exactly what we have seen from the above equatorial fluorine in this structure. So here we have this fluorine, they are numbered as a 1, in which this fluorine they are numbered as 2, which is lying in the equatorial position. So now if we consider, then we have two kinds of fluorine, that is fluorine numbered as 1 and fluorine numbered as 2. So we'll get 2 signal in the 19F NMR. Now if we talk about the area ratio, then for this signal in SF4 molecule, we have 2 fluorine of different types than that of this 2 fluorine. So we'll get the area ratio of 1:1, as because 2 fluorine of one type and 2 fluorine of two type, what we have discussed in this molecule. Similarly, talking about the multiplicity for this 2 fluorine of one type. Now considering this 1 fluorine over here, if we see the molecule from this side, then we will be able to see 1 fluorine at our side, that is this fluorine, and 1 fluorine which is lying below the plane, that is this fluorine only, not the fluorine which is lying at the back side. So this fluorine, it will couple with this 2 fluorine. So we will get a triplet multiplicity signal, that is 1 bond 2 bond coupling also. That is with 2 bond coupling we will get triplet multiplicity signal for this one type of fluorine, first type of fluorine. Similarly to another first type of fluorine will get the same environment. So for 2 fluorine of first type will get triplet multiplicity with this coupling constant, that is 2 bond coupling constant F1 for F1 due to F2 over here what we have discussed. Similarly for fluorine number 2 we will get the coupling constant due to this bond up to this bond over here, that is this fluorine number 2 it will couple with this fluorine number 2 via this 2 bond. So we'll get a multiplicity of this fluorine, it will couple with this number 1 fluorine from this side, another number 1 fluorine which is different from that of this fluorine number 2. So it will couple with the 2 fluorine, will get triplet multiplicity signal for the second type of fluorine with its coupling constant of 2 bond, that is given by like this over here. 2 fluorine of 2 type will get triplet signal, that is if we are getting the triplet signal for this fluorine then we will get exactly similar signal for this fluorine also. So we get triplet signal for 2 fluorine of second type and with 2 bond coupling constant, that is 2J F2 due to F1. So with this we will see another problem here, that is BRF5. In this the structure of BRF5 is as shown here, which is square pyramidal, that is the shape of this BRF5 is of square pyramidal, which is given by this bonding structure where we have one lone pair of bromine which is lying at the axial position along with this fluorine over here. So this fluorine which is at the axial position, which will be different from that of this fluorine which is lying at the equatorial position. So if we number the equatorial position fluorine as 2, then we will get the different environment for this fluorine, so we number this fluorine as a 1. So with that we got 2 different kinds of fluorine in this molecule, so we'll get 2 signal in the 19F NMR. So we have 4 fluorine in the equatorial position in this BRF5 molecule and 1 fluorine in the axial position. So 4 fluorine is to 1 fluorine, so we'll get like 1:4, that is 1 fluorine of first type and 4 fluorine of second type, which is over here. So we'll get the area ratio as like this 1:4. Now talking about the multiplicity for the first kind of fluorine over here, it will couple with this 1, 2, 3, 4 fluorine of different environment than that of this fluorine over here. Then we'll get quintet multiplicity signal with 2 bond coupling constant, that is 1 bond from this fluorine number 1 to bromine, then bromine to this fluorine number 2. So we have 2 bond, so we'll get 2 bond coupling constant. So with that we will get the 1 fluorine of first type with quintet multiplicity with their intensity ratio as 1:4:6:4:1, which is given by the Pascal's triangle area ratio, intensity ratio. Another one for this 4 fluorine which is lying at the equatorial position will get the multiplicity as this fluorine number 2, it will couple with this fluorine number 1 via this 1,2 bond. Now this fluorine over here, this is of similar environment than that of this fluorine, so it will not couple with this fluorine. Here also this fluorine will not couple with this fluorine over here, so it will couple with this fluorine which is at the totally different environment than that of this one. So it will couple with this 2, that is second kind of fluorine, it will couple with the first kind of fluorine via 2 bond. So if one of this second kind of fluorine is coupling to the first kind of fluorine in this molecule, then all these 4 fluorine they will couple with this first kind of fluorine. So 4F of second kind they will couple with first kind of fluorine to give a doublet multiplicity signal, that is like this over here. and if it is doublet, then we will have the array ratio as 1:1, which is given by the, that is intensity ratio of 1:1, which is given by the Pascal's triangle intensity ratio. With this, we have two different kind of spins in this, that is two different kind of nuclear spin, that is fluorine, 1 fluorine of first kind, 4 fluorine of second kind. So we'll get the Pople notation as AX4. Now along with this, we will consider another example in this, that is IF7. Now this molecule, that is IF7, it is of pentagonal bipyramidal, that is 2 fluorine will be in the axial position and the 5 fluorine they will be in the equatorial position. So with that, if we consider the bonding structure, we will have this structure as like this over here. Now not going to the very detail of this bonding structure, we will consider the type of fluorines. Here we have 5 equatorial types of fluorine and 2 axial types of fluorine, where this axial types of fluorine, if we number them as 1, then we can number this equatorial type of fluorine as 2. So we have 2F of, that is 2 fluorine of one kind and 5 fluorine of second kind. So we are thinking that we will observe 2 signal in the 19F NMR for this molecule, but at room temperature, the axial, that is axial and equatorial fluorine, they will be exchanging at a very fast rate. That is, we cannot observe which one is axial and which one is equatorial. They will be exchanging at a very fast rate to each other. So this molecule will show the fluxional behavior. All this fluorine at room temperature will be looking alike, that is, they will be of similar environment at room temperature. So we will get only one signal at room temperature, but at below 100, that is minus 100 degrees centigrade, we will observe the number of signal in 19F NMR as 2F, that is of one type, what we have observed here. They will couple with this 5 fluorine. Now we will get 6-state multiplicity signal that will be given by this intensity ratio, that is 1:5:10:10:5:1, which is given by Pascal's triangle. And for this 2 kinds of fluorine, that is 5 2 kinds of fluorine, we will get 5 2 kinds of fluorine, they will couple with this 2 fluorine and will get triplet signal, which is 1:2:1 intensity ratio. Now 6-state triplet, so we'll get the Pople notation as A2X5. Now we can consider another example. We have P4, that is, if we consider this phosphorus over here, in this phosphorus, that is P4 structure, this phosphorus will be directly connected to the 3 phosphorus atom. Similarly, the phosphorus over here, that is this phosphorus, it is also directly connected to the 3 phosphorus. So all these phosphorus are in the same environment, then they all are of similar kind of spin. So 4 phosphorus, they will give a singlet signal in 31P NMR. Now coming towards the Pople notation, we will have A4 for this molecule. Now if we put one oxygen to this phosphorus, then it will look like this over here. So for this phosphorus, now environment is different to that of this 3 phosphorus over here. So 2 kinds of phosphorus will get the signal in the 31P NMR, and for this we will have a Pople notation as AX3. Similarly, if we put another oxygen to this side, we will get 2 phosphorus of the same kind and 2 phosphorus of the another kind. we'll get the Pople notation as A2X2. With that, we can deal with this kind of molecule. With these examples, if you like my videos, don't forget to share it to your friends, giving thumbs up right down below. Thank you.